Hello everyone, this is Jagnesh. So see, last week's session, we discussed about the basic statistics. So the basic statistics in the sense, what is mean, what is median, what is the difference between mean and median, what is variance, what is standard deviation, okay? And using these four variables, okay, so we call that as statistics variables. Okay, using these four variables, how we can come up with a conclusion saying that, okay, so I do have something called, variable called salary, which has 30 samples in it. Okay, so how I can understand, how I can get a meaning from that variable. Okay, that is very important. Okay, so if I know the mean of that variable salary, okay, then I can come to a conclusion that, okay, so, more or less the values, the salary would be like this. For example, if the mean is 40,000, I can understand that, okay, more or less, people will get 40,000 salary. Okay, so then I'll see standard deviation. The standard deviation is 5,000. Then I can understand that, okay, the minimum salary would be 35,000 and the maximum salary would be 45,000. Okay, so it means the mean is 40,000. So when I subtract the standard deviation of 5,000 from the mean, I'll get 35,000. That could be the minimum value, minimum salary. And the maximum salary is when I add standard deviation to the mean, I'll get the maximum salary. So, so when you give me any variable, when anyone gives any variables like salary, whatever it is, okay, so I can understand the mean and standard deviations. Okay, they didn't give you the actual value basically. Okay, they said that there's some variable called salary, where the mean is 40,000, where the standard deviation is 5,000. Okay, so but they didn't give the actual value, the salary of each and every person. Okay, but they give mean and standard deviation. Okay, using this two value, using this two statistics variable, okay, you can come to know that how the real value could be. Okay, so that's basically the mean and standard deviations. Okay, think about the real case. Okay, in the real case, we get millions of data. Okay, is that possible that you can examine each and every data? It's obviously not possible. Okay, so that's why we have mean, median, standard deviation. Okay, so using that, we can come to a conclusion that the actual value should be like that. Okay, okay. So today's session, okay, would be more on distributions. Okay, for an example, okay, so obviously we have a question that what is called distribution. Okay, so the agenda, the synapses for today's trainings are distributions. So in statistics, there are multiple distributions available. Like starts with Bernouli, binomial, normal or Gaussian distributions, exponential distributions, uniform distributions. Okay, so obviously we do have many things. We do have many distributions available, but this session will first, make you understand what is distribution. Okay, so what are the different types of distributions and what are the major use distributions, and basically, what is the need to understand distribution to become a data scientist. If I want to work in machine learning, how this distribution would help me. So obviously, you have to, understand that. So that's basically our today's session. So the motto of the session is, okay. So obviously, this starts with a Bernoulli distribution. Okay. So the Bernoulli distribution is, okay. So first of all, before we jump into Bernoulli distributions, okay, let us understand what is distribution. Okay. So the distribution is, okay, we take the same example. Okay. We got a sample of 30 people. Okay. The sample is a salary. Okay, so we got the salary. Okay, so let me write everything in Notepad. Okay, so in today's session, what we'll do, we basically go through each and every example. For example, we'll go to the Bernoulli distributions. Okay, so we'll explain what is Bernoulli distribution, how it can be used. Then I'll show some simple examples in Python. Okay, so that can explain us how we can practically use this binomial normal distributions in a machine learning program. So that's how the session could be. Okay, so I'll just make a write up here. okay, in a text file. Okay, so in this write-up, I'll put everything that what we discussed today, what we're going to discuss today, what we discussed today. So at the end of the session, you can see this notepad. This notepad will explain you what are the concepts. We just go through. Okay, so that's the motto. Okay, so the first concept is what is basically distribution. Okay, so and why we need seriously. Okay, the answer is, okay, so let's take a sample from the real world applications. Okay, maybe in your company, okay, there may be 1,000 people are working. Okay, so for an example, we take some company, okay, some Indian company, IT company. Okay, so we select a sample from a particular department. Okay, so assume that let's take in 30 sample from IT company or particular department. Okay, let's take a sample of salary from IT company, particular department. Okay, so now from this, okay, if I write a plot, okay, so if I make a plot in this 30 samples, okay, then that is called distributions, and I'll tell you this. Okay, now what could be the salary? Okay, determine each and every value. So one of the salary is 40,000, another is 42,000, another is 35,000. Okay, so that's how it will go. Okay, so what is this basically? Okay, so obviously, as I said, this is if I have millions of sample, how I can make this a function wise things. For example, in a single function, I can understand what is going on the sample and what kind of sample this is. For example, through median, mean, variance, and standard deviation, I can understand what value it could be. But how it could be means, for an example, as we discussed, means as I said, the multiple distributions, right? And basically, each and every distributions are unique on their perspective. For example, normal distributions of a continuous variables, binomial distributions of a discrete variables. So obviously, through the distributions, I can understand that this will handle only discrete variables. This will handle only continuous variables. Okay, the nature of the data is like this. So that definition is nothing but the distributions. Okay, so as of now, just understand that when it gives the flavor for a data, through the data, I can understand that, what kind of variable I used, what kind of mean it could be. Okay, so basically, how I can give a mean basically, to give the mean, okay, to calculate the mean, to calculate the standard deviation, basically you need to understand the nature of the data. Okay, so when you understand the nature of the data, then you can apply some formula and you can calculate the mean, median, and standard deviation. Then you can come to the intuition saying that, okay, that's how the data could be. Okay, so to calculate mean, median, standard deviation, first of all, we need to understand the distribution. Okay, so when we understand the distribution, okay, then we can say that, okay, this will basically follow binomial or continuous or a normal distribution. Okay, so then we can apply the formula. We can calculate the mean, standard deviation, and variance. Okay, so then we can say that, okay, that's how the data is aligned. Okay, so that's why the distributions are very important. Okay, so first let us go through a binomial distribution. Okay, so then we'll come to this question again. Okay, so we would have a better understanding. First, understand binomial distribution. Okay, so what is exactly binomial distributions? Okay, so before we comes to binomial distribution, let me go to Bernoulli distribution. Okay, so Bernoulli distributions are output are either success or failure. Okay, it's basically two possible outcomes. Okay, so either 1 or 0, success or failure, true or false. Okay, so now let's take another sample. The sample is gender. Okay, so now the gender could be either a male or a female. Okay, so now if someone gives this sample to me, then I'll understand that this has only two possible outcomes, because either a male or female. Then obviously it follows the binomial distribution, means the Bernoulli distribution. Okay, because it has only two possible outcomes. Okay, that's what it will define. Okay, so when the distribution has only two possible outcomes, 1 or 0, or a success or failure, true or false, the male or female, that's nothing but a Bernoulli distribution. Okay, now take an example. Okay, the example is flipping a coin. A conventional example. Okay, so first let us discuss a very simple example, then we'll go to the critical examples. Okay, so when flipping a coin, what could be the outcomes? Okay, either a head or a tail. Okay, so basically it has two outcomes. Since it has two outcomes, it should be a Bernoulli distribution. Okay, so now when it toss a coin, okay, it could be either head or a tail. Okay, let us assume that we take the fair coin. Means fair coin in the sense, some of the coin would be a biased coin. Means biased coin in the sense, it will always be head. Most of the times would be head, because the nature of the coin would be something like that. So whenever you toss a coin, it might be, head always, or in some of the coin it might be tail always. Okay, so when I say fair coin, it should be 50-50% probability to get it head or to get it tail. Simple. Okay, now let us assume that we take a fair coin and we toss a fair coin. What could be the outcome? Okay, so either a head or a tail. So what would be the probability to get a head or tail? Okay, so I need to come up with a function. Okay, so when I toss a fair coin, what could be the probability to get a head or tail? Okay, so let us assume that the probability is P. Okay, so this is very important. So I can say you just understand each and everything. So let's come again. So we take Bernoulli distribution. Okay, so as I said that Bernoulli distribution have two possible outcomes. The outcomes could be 1 or 0, a success or failure, true or false. Okay, so we take a flipping coin example. Okay, we flip a coin, either we get a head or a tail, basically two outcomes. Okay, so we took a fair coin. Okay, and the probability for getting head is P. Okay, so what could be the probability to get tail? Probability to get tail. Can anyone answer? Just try. That's not a problem. So yes, the answer is 1 minus P. Okay, so now, okay, let us define a function for this. Okay, so now this is the data we get. Okay, the data we have with us. Okay, so it's a coin tossing example. Okay, so the possible outcomes are head or tail. The probability for getting head is P. The probability for getting tail is 1 minus P. Okay, so using that, we have to come up with a function. Okay, we can say that as of now the probability function. Okay, that should define the nature of the Bernoulli distribution. Simple. Okay, so in the first session we discussed two variables. Okay, so one is discrete variables, another is continuous variables. So within discrete variables there are two flavors, which is nominal, ordinal. Within continuous there are two flavors, which is okay, there are two flavors we have seen as of now. Let's not worry about it. Okay, let's make it small p. Okay, so now think about it. I toss a coin. Okay, now I get head. Okay, so the first example. Okay, I flip a coin. The first flip, I get head. The second flip, I get tail. In the third flip, get tail again. Okay, so now using this, okay, we'll try to define. Okay, so now you can say that out of a 3 flip, I get 1 head and 2 tail. And obviously, the probability to get head is 1 by 3. The probability to tail is 2 by 3. Okay, so out of 3 flip, I get 1 head. So I say the probability for getting head is 1 by 3. The probability for getting tail is, getting tail is 2 by 3. Okay, so then the probability of success is 1 by 3. The probability of failure, so we can say, the head is success. Okay, getting head is success, getting tail is failure. So the probability of getting head and the probability of getting success is 1 by 3. The probability of getting tail and the probability of getting failure is 1 minus 1 by 3, which is equal to 2 by 3. Very simple. Okay, so either you can use the formula or either you can use the common sense and come up with the direct answers. So it depends. If the situation is really simple, you can use common sense. Okay, you can basically come up with the answer. But if it is a little critical problem, even though you're aware of the fact, okay, obviously you need to apply the formula and come up with the answer. Okay, so now how we define this? Okay, so let's logically go with that. Okay, so the probability is P to the power of X. Okay, so the probability of getting head, power of the actual value. This is where we flip a coin. Okay, and then 1 minus P to the power of 1 minus X. Okay, so using this data, I come up with this formula. Let me explain you how I come up with this formula, how I arrive this formula. So when you define a probability function for a discrete variable, okay, then it is called a probability mass function, as we discussed or as we have seen in the last session. Okay, so when the variable is a continuous variable, then the probability function could be a probability density function. Simple. Okay, but when you become more and more familiar in statistics, when you go to the measure theory level, okay, as of now I've discussed about the statistic theory, but when you go to the measure theory level, you will be little mature and go to the measure theory level. Okay, in every sense, we call probability function as a probability density function, even though the variable is a discrete variable or a continuous variable. Okay, so we'll follow the measure theory notations, because when it comes to machine learning, okay, it should be a measure theory kind of concept. Okay, so as of now, we'll follow the measure theory notations. Okay, I call this a probability distribution function. Okay, so now let us apply this. Okay, this X is the head, this 1 minus X is the tail. Okay, so in the example, okay, we discussed above, means we 3 times flip a coin. Okay, 1 time we got head and 2 times we got tail. Okay, that is basically, so the probability of X means the X is nothing but we got 1 head, and 1 minus X is we got 2 tails. Simple. Okay, so when you replace, so the probability given 1 head and then 1 minus P to the power 2, because we know that the X is a discrete random variable. Okay, and 1 time we got head and 2 times we got tail. So when you replace this formula with the real value, then we got this P to the power of 1 into 1 minus P to the power of 2. Okay, so now this could be the probability distribution, the probability density function for the Bernoulli distribution. Okay, so now obviously either the probability would be a known probability or unknown probability. Okay, so someone will come to you and ask you to take the sample. Okay, and they'll say that, okay, on the sample, the probability of getting, okay, so assume that, in this way, okay, you're a developer, okay, and some business analyst comes to you and he'll give you some sample. Okay, means that the business analyst already come up with a sample. Okay, and he gives the sample to you. When he gives the sample to you, he say that, okay, this is basically a coin tossing example. Okay, and out of 30 samples, I get 20 heads and 10 tail. Okay, so the probability of getting head is this many percentage. The probability of getting tail is this many percentage. So the business analyst tells everything to you, means that is a known probability. So the business analyst gives a scenario or it gives a sample to you. When he gives a sample to you, he gives the probability as well. So now the scenario is sample with known probability. Okay, sometimes he may not give you the probability, and he can ask you to come up with the probability. Okay, that's basically unknown probability. We'll discuss that. Okay, if you ask me a question, how I can define a probability, or how I can find the unknown probability, we'll come up with that. Okay, but right now just understand the essence of the formula. Okay, the Bernoulli distribution formula is p to the power x into 1 minus p to the power 1 minus x. Okay, so the x is nothing but the success, the 1 minus x is nothing but the failure. Simple. Okay, so if you mean to say that, or you can in your scenario, the tail would be the success and head would be the failure. So then this x would be the tail and then 1 minus x would be the head. Simple. Okay, so it's better to denote x as a success and 1 minus x as the failure. Okay, since we have two possible outcomes, 1 minus success is nothing but the failure. Okay, so now what we're going to do then? Okay, so now we know that the probability density function of a Bernoulli distribution. Simple. Okay, so now I can find the probability of head. Okay, so what is the probability to get head? Or you can say that what is the probability to get tail? Okay, so when someone asks the question like this, okay, so before that you should know the probability. Means the probability of head or the probability of tail. Okay, so then when someone asks the questions, after that we can come up with that. Means, for example, in a fair coin, the probability of getting head is 0.4%, 40%, and then the probability of tail is 0.6%. We know that. Okay, let us take like this. Head is 1, tail is 0. Okay. If someone asks you, what is the probability to get head? So P is 0.4 to the power of 1 into 0.6, which is 1 minus 4 is 0.6, to the power of 1 minus x, which is 1 minus 1. So 1 minus 1 is 0. Anything to the power of 0 is 1. So it could be 0.4 power of 1 into 1, because as I said, anything to the power of 0 is 1, which is 0.4. Okay, and this is the probability of getting head is simple. We'll take the same formula. Okay, so x value is 0 here, x value is 0 here. Okay, so anything to the power of 0 is 1. Okay, so 1 into 0.6 to the power of 1, which is again 0.6. Okay, so when the probability is unknown, then we have to use the mean, median, and standard deviation value. Okay, so before to go into that, okay, let us put like this. Okay, what is the mean, variance, and standard deviation of Bernoulli distribution? Okay, that's the question. So anyone have the answer? How we can calculate the mean, variance, and standard deviation? Let us take mean. So how we can calculate the mean value? Maybe you can try, not a problem. Okay, so last time we discussed about the mean formula, right? What could be the mean formula? Okay, so either we call it as a mean or expected value. Okay, we say that as expected mean. Okay, So the expected mean is, what could be the expected mean formula? Okay, so if you have three variables, okay, then x1 plus x2 plus x3 divided to 3 is the mean. Okay, that's what we discussed last week, right? So the average value from the sample is nothing but a mean, or average population is nothing but a mean. So when we have three variables, the average is x1 plus x2 plus x3 divided by the number of samples is nothing but the average. Okay, so we can apply the same formula to the Bernoulli distribution. Okay, so the expected mean, or we can say the expected value formally, okay, of Bernoulli distribution is, okay, sum of x, the x is nothing but a sample, okay, to the probability of x. Okay, the sum of x into the probability of x. Okay, because to the probability only we can understand. Okay, so now we can apply the same formula. Okay, so we can take the distribution. Okay, so now here, when I say the expected value denotes success, not a failure. Okay, simple. So the x, what could be the expected value to get a success? Okay, simple. So now what could be the expected value now? Let's define a formula here. Okay, the formula is simple: p to the power of x into 1 minus p to the power of 1 minus x. Okay, so now what is the x value? The probability of success means, I'm sorry, the x value is the success value. The success value is 1, which is to the power of p to the power of 1 into 1 minus p to the power of 0, which is 1 minus 1 is 0, is equal to p. Okay, so the mean or the expected value of Bernoulli distribution is p. Okay, so the mean of Bernoulli distribution is p. Okay, so what could be the variance? Okay, so the variance is, okay, let me go with the variance formula. Okay, so the variance is basically, okay, so let us take the same example. Okay, let us assume that we come up with a mean value which is mu. Okay, so now the variance is the actual sample minus mu plus the second value minus mu plus third volley means third value minus mu. Okay, divided by 3. So this could be the mean value. Okay, otherwise how I can convert this into a different formula? Okay, so as of now I'm not going to derive this, I'm just telling you the formula. Okay, so that could be expected value of, because I know the expected value already, so using the expected value I have to derive the variance value. Okay, so the expected value of x square minus expected value of x of square is nothing but the variance. Okay, so let us use this formula and calculate the expected variance. Okay, so the expected variance of Bernoulli distribution is equal to, so we know what is e to the power means, I'm sorry, e of x means the expected value of x is p. So what could be the expected value of x square? Okay, means apply this formula here. So p to the power of x, which is nothing but x square, into 1 minus p to the power of 1 minus x square. Okay, so here 1 square into 0 square. Otherwise I can write this formula better. Okay, so e to the power of x square, which is equal to okay, this is the formula. Just now apply the apply the value here. P to the power of 1 1 minus p to the power of 0 is equal to p again. Okay, so e of x square is p. Okay, now let us calculate the e of x square. E of x square, which is, so we know what is e of x is. E of x is p. Okay, so p square. Okay, so now let us apply this value to the formula. Okay, so e to the power x square is p minus e to the power x of square is p square. Okay, so now I take a common value p, which is 1 minus p. So I like this. So now p into 1 minus p is the expected variance of a Bernoulli distribution. Okay, so now the standard deviation, how we can calculate the standard deviation from that. Okay, so what could be the formula for standard deviation? Okay, not a problem. The standard deviation is the square root of variance is nothing but standard deviation. So here the variance is p into 1 minus p. So the square root of variance is nothing but the standard deviation to the power of 1 by 2. Simple. Okay. So now how we define the formula is very important. Okay. So first we come up with the nature of the variable. Okay. So the variable is a success or a failure. So either it be a 1 or 0. Okay, and then obviously we take a fair coin. Okay, either we make it a biased coin or a non-biased coin. That's not a problem. So obviously the probability of getting success is p, and obviously we can, from that we can define the probability of getting failure, which is 1 minus p. Okay, so using this concept we come up with a formula p to the power of x into 1 minus p to the power of 1 minus x. Okay, so using that we come up with the expected mean, expected variance, and a standard deviation. Okay, so who ask you, okay, what is the mean, variance, and standard deviation of a Bernoulli distribution? You can say that p is the mean of a Bernoulli distribution, 1 minus p is the variance of the Bernoulli distribution, and standard deviation is the square of p into 1 minus p is the standard deviation basically. Okay, now let us discuss the binomial distribution. Okay, so if you see our presentation, the Acadgild presentation, it doesn't have the explanation about a Bernoulli distribution. Okay, we started with the binomial distribution. Anyway, that's a good starting point. But if we know Bernoulli distribution before binomial distributions, it is easy to understand. Okay, so I can say the generalization of Bernoulli distribution is a binomial distribution. Okay, so maybe you can ask the question, right? Okay, out of 5 samples, what is the probability for getting 3 success? Okay, so that's what the real world question is. Okay, so can Bernoulli distribution answer that? Obviously not. You know, it can say that, okay, if you have 5 samples, or if you have 10 samples, if you have 100 samples, whatever it is, okay, you have to say the probability, and then you can use this formula and you can get the answer. Simple, it wouldn't say anything other than that. But now my question is, okay, so I have 5 samples. Out of 5 samples, okay, what is the probability to get 3 head? Or what is the probability to get 4 head? Or what is the probability to get 5 out of 5 head? Okay, so obviously we'll ask that kind of questions, right? Okay, so obviously we have to generalize a Bernoulli distribution. So we can say the generalization of Bernoulli distribution is nothing but a binomial distribution. So means binomial distribution is ditto same to the Bernoulli distribution, but it is a generalization. It provides a generalization to the Bernoulli distribution. Okay, that's nothing but the binomial distribution. Okay, let us go to the slide now. Okay, so in the binomial distribution, we have fixed number of trials. Okay, how many trials I tried? Okay, so trials in the sense samples. Okay, out of 5 samples, we say 5 samples, right? So that's nothing but the trials, which is the n value. Okay, out of 50 samples, which is 50 is there. Okay, out of 1000 samples, 1000 is the n. Okay,
So it strictly follows the Bernoulli distribution. So obviously each trial has two possible outcomes, either a success or a failure. So the probability of success is P and the probability of failure is 1 minus V for all trials. And all trials are independent value, means independent in the sense, okay? So we do have, assume that we have 5 samples, and the second sample is independent to the first, third, fourth, and fifth sample. Okay, that's completely independent, and every value follows that. Simple. Okay, that's independent. Okay, so now we define the probability distribution function for a binomial distribution. Okay, as we already discussed. Okay, let us put like that way. Okay, the generalization of Bernoulli distribution is binomial distribution. Okay, so this is very important. So the generalization of Bernoulli distribution is binomial distribution. Okay, so now I have n trials. Okay, so out of n trials, what is the probability to getting success? It's my question. Okay, so we'll call that as n choose x. N choose x. Okay, or we can say that n of x. Okay, so that's where we give in the PPT. So this particular factor is n choose x. Okay. Okay. So what is the formula for n choose x? Okay, the formula is n factorial divided by x factorial into n minus x factorial. Simple. Okay. So maybe we can come up with some example. Okay, let us take an example like this. Okay. What is 5 choose 3? Okay. So 5 factorial divided by 3 factorial, which is x, and 5 minus 2 is 2 factorial. Okay, so 5 is 5 into 4 into 3 into 2 into 1 divided by 3 is 3 into 2 into 1 into the 2 is 2 into 1. Okay, so now 5 into 4, which is 20, 20 into 3, which is 60, 60 into 2, which is 120, divided by 3 into 2 is 6, and 6 into 2, which is 12. So now the answer is 10. Okay, so we have 5 trials. Okay, so out of 5 trials, what is the probability, okay, for getting 3 success? Okay, otherwise let us put like that. Okay, I have 5 trials. Okay, let's take the same example, flipping a coin. Okay, I flipped the coin 5 times. Okay, so first flip, second flip, third flip, fourth flip, fifth flip. Okay, out of 5 flip, what is the probability to get getting 3 head? Okay, like that. Tail, head, head. It's like head, head, tail, tail. This is one way. Head, head, tail, head, tail, 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 head, 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 like that. Okay, so basically I have 5 trials. Out of 5 trials, what is the probability to getting success? To getting 3 head. Okay, so how many times we will get? Okay, that's basically the question. So now, what is 5 choose 3, which is 10, 10 into. Okay, let us assume that the probability of head is 0.4, as we seen in previous example. Okay, the probability of getting tail is 0.6. Okay, so we'll apply the same formula here. Okay, so 0.4 to the power of x, which is x is 3 here, because we need 3 heads. Okay, into the probability of getting tail is 0.6 to the power of 5 minus 3. So just 10 into 0.4 power of 3 into 0.6 to the power of 2. Okay, so when you substitute this, obviously you'll get an answer. Okay, let us substitute. Okay, so let me open a calculator. So 10 into 0.4 to the power of 3 into 0.6 to the power of 2, which is 0.234. Okay, so the probability of getting 3 head out of 5 trials is 0.23%. Okay, so as of now, we will again, we'll see what could be the mean, variance, standard deviation, as like Bernoulli distribution. Okay, so but before that, okay, let us now calculate the mean, variance, and standard deviation. Okay. Okay, so anyway, this is the generalization of, since the binomial distribution is the generalization of Bernoulli distribution, let us substitute the value directly and then we calculate this. Okay, the mean is P, the standard deviation is P into 1 minus P. Okay, and the standard deviation is square the root of variance, which is to the power of 1 by 2. Simple. So now how we can generalize this? Okay, so what is the additional point we consider when we generalize the Bernoulli distribution? Okay, the only point is n choose x. Okay, so out of n trial, what is the probability of getting success? What is the, and out of n trial, what is the probability of getting failure? Okay, so now when I substitute n here, that's basically the generalization. Okay, so the mean of binomial distribution is n into p. The variance of binomial distribution is n into p into 1 minus p, and the square root of variance is nothing but the standard deviation. Okay, so now we have to calculate one thing, which is the probability density function of a binomial distribution. Let us define that. Okay, probability density function of a binomial distribution. Okay, so before that we have to, again, we have to come up with that. The generalization of Bernoulli is binomial. So the Bernoulli probability density function is, okay, so p to the power of x into 1 minus p to the power of 1 minus x. That's nothing but Bernoulli distribution density functions. Okay, so how we can generalize this? So as you all know that, okay, in Bernoulli there is only one trial. Okay, but in binomial we have n trials. So let us rewrite this. Instead of 1, we'll put n because we have n number of trials. Okay, and then we also has to put, okay, the n choose x. Simple. So the probability density function of a binomial distribution is n choose x. So you know what n choose x is. The n choose x is n factorial divided by x factorial into n minus x factorial. You can substitute this into the Bernoulli distribution probability density function. Instead of 1, we put x because we do have n trials instead of 1 trial. So guys, I understand that it could be a little difficult to remember all things. Okay, so but when you understand this basic, then machine learning is nothing for you. Okay, so after we discuss Bernoulli and binomial, I'll tell you how they come up with logistic regression using Bernoulli distribution. Okay, so for logistic regression, the Bernoulli distribution is the key. Okay, so if you understand Bernoulli distribution, then logistic regression is nothing for you. Okay, you can easily understand. So obviously I'll explain that. So now we have to calculate the mean. Anyway, so we already calculated the mean, variance, and standard deviation of a Bernoulli distribution, which is the mean is n into p, the variance is n into p into 1 minus p, the standard deviation is the square root of variance. Simple. Okay, so when someone asks you to compare a Bernoulli distribution and binomial distributions, you can say a single word: the generalization of Bernoulli distribution is nothing but a binomial distribution.
Okay, so when it comes to generalization, the number of trials is the generalization factor. So it comes in front of mean, variance, and standard deviation, as well as the probability density function. Simple. Okay, so now let us go to some examples. Okay, so then how then we can discuss that how the Bernoulli distribution is the influence of logistic regression, because that could be very important to you people. So when it comes to machine learning and data analysis, you can generally put the statistical concept to understand machine learning and data analysis, because that could be the base for you. Okay, so okay, now let us go to examples. Okay, so in the example, I didn't mention how we can calculate mean, how we can calculate variance, how we can calculate standard deviation of a binomial distribution. Okay, so I just put a simple example in such a way that how the binomial distributions is used in the real Pythonic code. Okay, so I didn't want you to concentrate too much on programming. Okay, so as of now, when you understand the concepts, okay, so you have to understand how in the Pythonic world or in the data science world binomial distributions are used. Okay, so now let us put like this. Okay, so as we discussed, okay, so when I have a discrete variables with bunch of samples, because the n samples, obviously I cannot give you all the values, okay, because that's not possible in the real time. Okay, instead what I'll give this number of trials as well as the probability. Okay, so if I give this, then you have to generate a random variables. Maybe if you want to generate the 10 random variables or 10 samples from the number of trials and the probability. Okay, that's as per your wish. Okay, so that's what. So this example particularly tell us how I can create a discrete binomial random variables using the value of n and the probability. Simple. Okay, let us first call the NumPy package. Okay, in Python, this basically for statistic linear regressions, or gradients, basically NumPy is the good package. Okay, so this basically very good for matrix and tensor operations. Because now we have the number of trials is 10. Okay, the probability of getting success is 0.5. 1 minus p is the probability of getting failure, which is also a 0.5. Okay, so now I call this NumPy random binomial distribution. Okay, so I said this is my number of trials, this is my probability. I just want to get the 10 samples from it. Okay, then I print this. Okay, so I'll just run this again. Okay, so let me restart the kernel. Okay, so the first line and the second line and the third line. So now you can see that I get a 10 binomial distribution random variables. Okay, so the first value is 2. Okay, so means I get 2 head, I get 6 head, I get 4 head, and a 4 head again, a 3 head, a 7 head, 5, 6, 2, 4, something like that. Okay, so this is basically a binomial random variables. Okay, so let us take a real world example. Okay, a company drills 9 wildcat oil exploration wells. Okay, so each with an estimated probability of success 0.1. So now assume that all 9 wells fail. It doesn't produce any oil. Okay, so what is the probability of that happening? Okay, so even though we say the probability of success is 0.1, okay, but all 9 will fail. Okay, so now we have to understand what could be the probability to get the 0 positive result. Simple. Okay, so assume that we got 20,000 trials and 20,000 samples of the model. Okay, and we have to get the probability of the 0 positive results. Okay, let us take this. Because now to get a 20,000 trials, okay, we have to use this function numpy.normal.binomial. Okay, and we have to give a value, the number of trials, which is 9 wildcat. Okay, and the probability of success is 0.1. Okay, so when we get a 20,000 trials, so now this will give the 20,000 trial to us, this simple function. Because now the question is, what is the probability to getting the 0 possible results? Okay, so that's why I said whenever this trial produced zero positive results. Okay, so here we see we don't have any zero positive results, right? Means we don't have any zero here. Means everything is positive. It's greater than zero. So obviously to get zero, we'll come up with like this. Okay, so out of 20,000 trials, how many trials gives a zero value? Okay, and then sum of those divided by normalization is the answer. Okay, so let me run this. Okay, so 0.39. So 39% is the probability to get the zero positive results. When the probability of success is 0.1 out of 9 trials. Okay, let me delete this. So any doubts on this example? No, it's simple. I didn't do anything rather than a simple thing. Okay, so anyway, when you take binomial distribution, the probability and the number of trials are very important. Okay, so when someone give me the number of trials and the probability of getting success, then I can generate whatever the number of binomial random variables. Okay, so here I generate 10 binomial random numbers. Here I get 20,000 binomial random number, but here my motive is to get the zero value. So I'll get the equal to sign. Okay, I know that you're familiar in Python, so you know what equal to means to. Okay, and then divided by the normalization factor, get this probability. Okay, so now let us discuss the motivating factor of logistic regression. Okay, so let's define like this. Okay, motivation behind logistic regression. Okay, so now let us think about the logistic regression. So logistic regression is also a classification problem. It's classification in the sense either the outcome is 1 or 0 or 1, 2, 3. Okay, so it's not continuous, it is discrete, simple. Okay, so now let us, for an example, let us take a very simple case. Okay, so now I have to understand. Okay, so now we are discussing the motivation behind logistic regression. We already discussed about Bernoulli and binomial distributions. Now, why we need binomial and Bernoulli distribution for this class? Obviously, you can ask the question. Okay, so instead I can directly go to logistic regressions and I can try the real world examples. Okay, so but obviously we derive the logistic regression cost function or objective function from a Bernoulli distribution. Okay, so first let us take a solid example to understand logistic regression. Okay, the example is the probability of winning the cricket match. Okay, so the probability of, or I can say that whether this match is win or loss. Okay, so basically this is the motivation behind. Okay, so the solid example is I have to predict whether I can win the match or lose the match, or whether India can win the match or lose the match. Something like that. You can ask any questions within this example. Okay, so for example, for that I need an input. I'll give the input, then I'll hit the logistic regression model. That will give me the output. That will be either win or loss. Okay, so anyway, when we discuss about in the machine learning class, we'll discuss everything. Okay, so as of now, I'm not going to discuss anything about logistic regression. Rather than one concept, just motivation behind logistic regression or a logistic classification, objective function, objective or cost or loss function. I think you can use loss function, that would be easy. Okay, so now let us first write the logistic regression loss function, which is sum of, okay, so for simplicity, let's not write sum. Okay, let's write this. This is the formula for logistic regression. x into log p plus 1 minus x into log 1 minus p. Okay, so now you ask me a question, how do you derive this formula? Okay, as I said, I derived this formula using Bernoulli distributions. Okay, let us recollect the Bernoulli distribution probability density function, Bernoulli PDF, which is p to the power of x into 1 minus p to the power of 1 minus x. Okay, let us apply log function here. Okay, log of Bernoulli PDF. So log of p to the power of x plus log of one minus p to the power of 1 minus x. Okay, so if you don't know the log probability, that is not a problem. Okay. Okay, so now, okay, so log is basically the vice versa of exponential function. Okay, so this will come from here. Okay, so x, the log of p, because there is something called power function in log. Okay, or a power log function. Okay, so when it basically has a power, so it means something like this. Log to the power of 2. Log to the power of 2 to the power of 3 can be rewritten like this. Okay, 3 into the log to the power of 2. This is basically a power rule of log function. Okay, so if you search in Google what is the power rule of log function, you'll get this answer. Okay, this is the basic mathematics. So we'll apply the same power rule. Okay, so we'll get this x front here, x into log to the power of log of p plus, okay, we'll get this power in front again, 1 minus x into log into 1 minus p. Simple. So now just compare this function and this function, the same. Okay, so now this is how we'll derive the formula. Okay, so first we set a problem. The problem of logistic regression is a binomial because it has two possible outcomes, either a win or a loss. Okay, now go to the statistics concepts. Okay, in statistics, what is the exact same thing available? So we know that is binomial or a Bernoulli distribution. Okay, so in a Bernoulli distribution, we know the probability density function. Okay, so we take the same probability function, we apply the log to the Bernoulli distribution, and we got the logistic regression cost function. Simple. Okay, this is how it is. Okay, so if you understand this, okay, if you able to link the statistics and machine learning, then you're the master. Because if you understand this concepts, because in the market, okay, there are very few people who can connect the Bernoulli and the logistic cost functions. Because they can understand logistic cost functions. And if you ask them what is the objective or a cost function of a logistic regression, they'll tell this formula. But you ask the same question, that how we derive this, they wouldn't have the answer. Okay, because they didn't well connect the machine learning with the statistics. That's the problem. Okay, so but if you're able to connect the statistics with the machine learning, then everything's simple for you. Okay, because see, the data science domain is not stable now; it is unstable. Okay, data science is just kicking off now. Okay, so but obviously after 10 years, it will be very good when compared to when compared today. Okay, so after 20 years, it will be much wider than we compare today. Okay, so it is obviously going to improve. Someone will come up with some classification rather than logistic regression. Okay, it might work well than logistic regression. Okay, so but otherwise, you may also have a problem that some binary classification. You have some examples about you have some problem. You have some binary problem. You apply logistic regression. You didn't get very good result. Okay, you tried all those parameters, but didn't get the very good results. Okay, then how you can get the very good results? How you can get the good results? Basically, you have to use the statistical concepts. You have to do some penalization in the logistic regression, and you have to get the output. Okay, so obviously, to get some good output, obviously you need a statistic concept. Okay, so that's why statistics is very important. If you understand statistics, then machine learning is nothing for you. You can very easily understand machine learning. So that's all about a Bernoulli, a binomial distributions, as well as we discuss about the motivation behind logistic regression, how to use Bernoulli distribution converted into a logistic regression cost function. Okay, plus we have seen some examples about a binomial distribution, how we can get a random binomial variable from the mean by using the number of trials and the probability of success using a NumPy binomial function. Okay, so plus we have seen a practical application, means a very simple practical example as well. Okay, now let us discuss a Poisson distribution. Okay, so now I ask, before we enter into Poisson distribution, I ask a question to you guys. Okay, so my question to each and everyone, just to make sure that you guys participate in that. Okay, so can someone tell me what is the difference between Bernoulli and binomial distribution? Okay, so the Poisson distribution is, okay, it is also the family from binomial distribution. Okay, so you know what binomial distribution is. Okay, so binomial distribution is basically came from a discrete random variable. Simple. So we have two random variables. One is discrete and continuous. Okay, so when I able to group something which is basically discrete. Okay, so either it will be 1 or 0 or 1 or 2 or 3. It has some specifications. Okay, so in the grouping limit, that's nothing but a discrete random variable. Okay, so we call binomial distribution as a family of discrete random variables. So Poisson distribution is also a family of a discrete random variables. That is also came from family of discrete random variables. Okay, so to derive the probability density function of of Poisson distribution. Okay, so how we derive the logistic regression cost function? We basically take Bernoulli distribution and then we apply log function, come up with a logistic regression cost function, right? Like that, we have to use binomial distribution probability density function. Okay, and then we have to apply some concepts. Okay, and then we have to come up with the Poisson probability distribution, means distribution or density function. Okay, so from now on, we are not going to derive any formula. For example, like we derive binomial distribution probability density function. From that, we calculated means, we derive mean, we calculated variance, we derive that, we calculated standard deviation. Okay, so we derive each and everything, right? But obviously, in the later section, we are not going to derive anything. We're just going to say the formula, that this is what the formula is going to be, and how we can calculate something which is by using the formula. Simple, because if you derive each and everything, then obviously that's not a good practice. Okay, so what is my recommendation to you? Okay, so if you're more interested in statistics, okay, so what you can do basically after this session, you just see how they derive the Poisson probability density function using the binomial distribution. Okay, so anyway, it could be a very simple concept. They apply some integration or a differentiation or some log function. They come up with this. Okay, so just go through this. Now we'll discuss about the Poisson distribution objective. Okay, the objective of Poisson distribution is, okay, so now take this example. Maybe we can take the same example of a cricket match. Okay, so on power play, okay, what is the probability of getting 50 or more runs? Or in power play, what is the probability getting 2 wickets? Okay, so like that, if you have a question like that, okay, so you do have a number of matches, right? So there are multiple matches between two countries. Okay, they play a lot of matches. Okay, so they in the power play, some scenario would occur. Obviously, they do have some patterns in the power play. Okay, so to use those patterns. Okay, and from that, ask the question like what is the probability of getting 2 wickets, or getting 3 wickets, or getting 4 wickets in the second power play and the third power play. Okay. Otherwise, let us take a very simple example. Okay, it's a conventional example. So if you go to website, they'll obviously tell these examples to you to make you understand Poisson distribution. Okay, the example is in a particular road, okay, on daily basis, between this time to, from time to to time, the 100 vehicles are crossing. Okay, so now from that you collect samples. Okay, so for 10 days or 20 days, okay, and you have samples with you. Okay, now you can ask the question that what is the probability, okay, of crossing 120 cars tomorrow, okay, or what is the probability of crossing 80 cars tomorrow. Okay, so this is what the Poisson distribution objective is. Okay, so I collect the samples, okay, in a particular scenario. Okay, this is basically, you know, discrete random variables, right, in a binomial scenario. Okay, so I have a samples with me. Now using the samples, I'll ask a question in such a way that what is the probability of getting this tomorrow or in future or in past as well. Okay, that's nothing but the Poisson distribution. Okay, this is basically the objective. So to keep this objective, we'll discuss about the probability density function and other things as well. Okay, so now let us go to the slide. Okay, let us. So as we discussed, Poisson distribution is also the family of discrete probability distribution, which is already discussed. Okay, so these are all some examples. The number of cars arriving at a service station in 1 hour, the number of flags in poles of a clock, the number of accidents in one day at a particular street stretch of highway. So these are some examples. Okay, so but we mostly concentrate on probability density function. Okay, so the probability density function of a Poisson distribution is e to the power of minus mu. This mu is nothing but a mean of a Poisson distribution into mu given by the discrete random variable divided by x factorial. Okay, so where the mean and the variance are same in case of Poisson distribution, which is mu. Okay, so you know the standard deviation anyway. Okay, so if you calculate the variance, the square root of variance is nothing but a standard deviation. The square root of mu is the standard deviation. So in Poisson distribution, the expected mean and the expected variance are same, which is mu. Okay, and the probability density function of a Poisson distribution is this: e to the power of mean means minus mean, a mean to the power of x divided by x factorial. Simple. And they'll give some examples here. Okay, the example is, okay, so let me read it very shortly. Okay, so I have 100 page of a textbook. Okay, and when I analyze this textbook, or when I analyze this 100 pages of textbook, okay, so I find a mean, okay, that behaves a Poisson distribution, or that behaves like Poisson distribution, okay, with a mean of 1.5, means the error mean of 1.5 that behaves same like Poisson distribution. Okay, simple. Okay, so I have a textbook. Okay, so you know when I go through the first 100 pages, okay, I'll find the error with a mean of 1.5. Simple. Okay, so now think this scenario. So I have a textbook. Okay, so I'll go through the 100 pages. Okay, so like that I have multiple textbook. So I'll go through all 100 pages. Okay, so then get the error. Okay, so on the first textbook, when I go through the first 100 pages, I'll get the error. Okay, and the second textbook, I'll go through the 100 pages, I'll get error x2. Like that, you get so many errors from so many samples, and when you average the error, okay, you'll get a 1.5. Simple. Okay, so now we can tell that what distribution it is. This is basically a binomial or a Poisson distribution, a discrete distribution. Okay, so now the question is matters. Okay, so now the instructor randomly select 100 pages of a new book. Okay, that's not from my sample, but same like my sample. What is the probability that there are no typo errors? Okay, this is the question. So now I have the binomial distribution variables. Okay, and ask the question. The question is, what could be the probability that I can randomly select a textbook and then randomly go through 100 pages, but the typo error is 0? What is the probability? So the distribution is a Poisson distribution. So you can take the probability density function of the Poisson distribution. So the probability of 0 is
u to the power of minus u, which is minus u is 1.5 into 1.5 to the power of 0, because we asked the question that a 0 typo error divided by the 0 factorial. The 0 factorial is 1. And when you apply this formula, okay, so when you just give it to this calculator, okay, so you'll get a 0.2231. Means there's about nearly 22% that we won't get the typo error. Simple. So this is what the Poisson distribution is. So we do have a probability density functions. Okay, so we do collect the samples. Okay, we do collect the trials. Okay, and then we calculate the mean value. Okay, that is a typo error 0.5. Then from that, so now we have all the statistics variables with us. Okay, so now we ask the question that what is the probability to get this? For that we use Poisson distribution, come up with the answer. Simple. Okay, so like that we have some examples. Just go through that. Okay, so now we'll go to one more examples in Python regarding Poisson distribution. Okay, so our example is basically how we can collect the samples from a Poisson distribution. Okay, so I want to collect 2 samples, okay, of a Poisson distribution with a mean value of 5. Simple. When I print this, I'll get 2 Poisson random variables, which are 6 and 1. Okay, so I use NumPy. So when I ask a question, the NP that randomly select a Poisson variable from a Poisson distribution with a mean value of 5, I'll get 2 values. Okay, so I'll write this. I'll plot a Poisson in a histogram plot. So I do have another a library called matplotlib, because I imported this matplotlib. Okay, so then I'll use this histogram plot. Okay, this S is nothing but a Poisson distribution random variable. Okay, so now I'll just get I'll get this random variable and I'll come up with the 14 histogram. A simple, like how many times I get the value of 2, how many times I get the value of 4, how many times I get the value of 6. You know, what is the probability to get the value of 6? What is the probability to get the value of 8? What is the probability to get the value of 10? That's what I fit in here. Okay, so this is how we practically use this. If someone asks you, okay, say I have to do some scenario, okay, as basically same like Poisson distribution, because what you can do basically, okay, to generate some millions of Poisson random variable. So on that is a sample basically. So on that sample, apply this kind of scenario and come up with the answer. If someone asks you like that, basically you can use this. Okay, so using this formula, you can generate millions of samples. Okay, then you can apply whatever the scenario, whatever the machine learning algorithms, you can come up with this. Okay, so now we have covered 3 distributions: Bernoulli distribution, binomial distributions, and Poisson distributions. Okay, and then the very important distributions, which is the normal distribution. Okay, so the first 3 distributions from the family of discrete variables. Okay, so the normal distribution came from the family of continuous random variables. Okay, so we can say, okay, so right now I put a point like this. Okay, I set a scenario like this. In the real world, okay, when you collect more and more samples, any distribution that follows a discrete random variables or a continuous random variables, whatever it is, okay, that also follows the normal distribution. Simple. Okay, what I mean to say, if I collect more and more samples of a Bernoulli distribution, okay, then it becomes a normal distribution. Or we can say that it behaves same like a normal distribution. When I collect the samples from a Poisson distribution, because when I collect more and more samples, that will behave same like a normal distribution. Simple. Okay, so now we set a constraint like that. Okay, the constraint is, even though it's a Bernoulli distribution, even though it is a binomial distribution, even though it is a Poisson distribution, when I collect more samples, then it will behave same like a normal distribution. So if I understand normal distribution, but because anyway in the real world we'll collect more and more samples. Okay, so we won't do any solution with a very less number of samples in the practical world or in the corporate world at least. Okay, so maybe academically it is very different. They may do some process with very minimum samples, but in the corporate world we do everything with a large samples because we do have enough data with this. Okay, so obviously I'll always do anything with a larger number of samples. Then obviously, let's take my point. Okay, so if you have larger number of samples, then any distribution would follow the normal distribution. So if I understand the normal distribution, then I could do anything. So that's the point. So, I try to emphasize that the normal distributions are very important. Okay, so that's why I told those examples to you. So if you understand the normal distribution, then you can understand other distributions as well. Okay, this is very important. So as I said already, the normal distributions came from the family of continuous random variable family. Means, okay, so it could be any value from minus infinite to infinite. Okay, so if it is a discrete variables, I can say that, okay, the value range from 1 to 2, or the value range from 0 to 5, or the value range from 10 to 100. But in a continuous, the random variable can take any value, which is minus infinite to infinite. Okay, so this could be the very good, example to understand what is discrete and continuous random variable. Okay, so first we'll discuss, so since it is a very important distribution, I'll discuss each and everything. Okay, so again, as we already discussed that, I'm not going to say how we derive the probability density function of a normal distribution. Okay, let us not going to discuss that. So let us continue normal distributions in the next session. So till then,